Welcome back. This is the second video in the fiber optic series. A link to the first video is in the description below for those of you who may be new to this channel and haven't seen the first videos yet. Please don't forget to like and subscribe so that you'll be alerted when new videos are released. In traditional copper lines, we use electricity to transport our data. With fiber optics, we use light. This light is within the infrared spectrum, using wavelengths of 850, 1300, and 1550 nanometers. In figure 1, we have a representation of a fiber optic cable. The core is in the middle of the cable, shown as a yellow dot. This is where light travels. The core is surrounded by the cladding. Both the core and the cladding are made of silica glass, the most pure form of glass. The next layer surrounding the cladding is the buffer. The buffer has no optical function. Its sole purpose is to protect the cable from physical damage. The last layer is the jacket. The jacket serves to protect the cable from external elements like rain and snow. There are two types of fiber optic cables, single and multimode cables. Single mode is used for long distances and multimode is used for much shorter distances. We are going to start today talking about multimode fiber optic cables. Now here are the different types of multimode fiber, ranging from OM1 all the way down to OM5. Now OM1 has a core diameter of 62.5. This one came out in 1980. This is the oldest type that we have. And this one has a core diameter of 62.5 microns. Microns is the same with micrometers. Now all of the others got a core diameter of 50 microns. But the cladding is all the same for all of them. Now the bandwidth here for OM1, it says 200 megahertz per kilometer. This simply means you can get 200 megahertz of bandwidth up to a maximum distance of 1 kilometer. And OM2, 500 megahertz over 1 kilometer. Beyond that, the speed would obviously drop, and the further you are away, the more the speed would drop. And here's 2000 megahertz, the same deal up to 1 kilometer, and here's 4700 megahertz. And lastly, for OM5, we got 5000 megahertz per kilometer. So anything over 1 kilometer, the bandwidth would drop, and the further you are away, the more that bandwidth would drop. For the wavelength, for OM1, you could use 850 nanometers or 1300 nanometers. Now this is the wavelength that you could send over OM1. Okay, 850 nanometers is the short wavelength and 1300 nanometers is the longer wavelength. And you could use LED or VCSEL. Now VCSEL stands for vertical cavity surface emitting laser. That's vertical cavity surface emitting laser. Now this is a laser and this is just an LED. We're going to be talking much more about this later. Now for OM2 we have 850 nanometers and 1300 as well, also using LED and VCSEL. Now for OM3 just use 850 nanometers only, and it used VCSEL for that. So it's OM4. OM5 is the newest one. This one came out in 2016. It uses 850 nanometers and also 910 nanometers. And it also uses additional wavelengths as well. Now for OM1, you'll notice that the speeds are not great. It supports 1 gigabit per second up to 275 meters and is not recommended for higher speeds because of modal dispersion. We haven't talked about this as yet. We're going to be getting into this later, but modal dispersion basically causes errors. This is errors that are created in your data Next, for OM2, you'll notice that the speed is better. You get speeds 1 gigabit up to 550 meters, which is greater than 275. And at 10 gigabits per second, you get 82 meters. And for OM3, 1 gigabit, 300 meters, and 10 gigabits, 300 meters. As you can see here, with the newer cables, the speed and the distance get better. It also got much better with OM4. OM5 is optimized for WDM, which stands for wavelength division multiplexing, and we're going to be talking much more about this. Now here I have a laser or LED, which will be sending light into the core. Now an LED is used for the older type multimode fiber cables like OM1 and OM2, but the newer ones use a laser. Now light travels at 300 million meters per second. This is light in a vacuum, and it's called refractive index 1. This is like light in free space, traveling pretty quickly. As light enters into glass, which is what the fiber cable is made of, the light slows down to 1.47. 1.47 is slower than 1. This slows the light down. So you have a refractive index of 1.47. The light doesn't travel as fast as this. It may travel around 200 million meters per second instead of 300. And now this is the cladding up here, and it has a refractive index of 1.45. The cladding is a bit faster than the core. The material in the cladding allows light to travel faster than it does in the core. But light is not supposed to travel in the cladding. Light is supposed to stay in the core. But they dope this area slightly differently. The purpose of this doping is to stop the light from traveling right through the glass. So when light gets to this point, between the core and the cladding, it is reflected back into the core, and whenever it gets to the other side, it is reflected back in. We're going to be talking much more about this, but I just wanted to touch on this right now so that you don't have any misconceptions of exactly what is happening in here. Okay, so when light travels through the core, it doesn't get out, it stays inside, and we refer to this as total internal reflection. Whenever light enters a fiber, it doesn't matter if it's coming from a laser or LED. It enters at an angle. This arrow here represents a 0 degree point, just going straight down the middle of the fiber. That's 0 degrees. Now, the light coming into the fiber optic cable always enter on an angle. Now here we see this cone-shaped light entering between 0 and 13.9 degrees in this case. Okay, so it's 13.9 degrees this point, so it's going from 0 to 13.9, so it's on an angle. It's never just straight down the fiber. Okay, so how we calculate this angle is by using the core's refractive index, which is 1.47, and the cladding refractive index, which is 1.45. We call them N1 and N2. So here we have N1 square minus N2 square, and then we take the square root of that. Here we got the 1.47 square minus 1.45 square, square root of that, and our answer here is 13.9 degrees. So this is called the angle of acceptance, which is 13.9 degrees. This could change depending on the refractive index. The refractive index can be anywhere between 1.44 right up to 1.48 for both the cladding and the core. So this could change depending on the values you have in here. In this case, it is 13.9 degrees. This angle is very important because everything else that happens within the fiber depends on the angle that the light enters at from the laser or the LED. So this is very important. If you get this wrong, everything else will be wrong. So I'm going to have to end this at this point because this particular video is getting a little bit longer than I would like. I'm trying to keep them all at a decent length. I don't want to get them too long. So we'll continue this topic in the next video. This is Trevor from Telecom Training. Please don't forget to like and subscribe if you haven't done so as yet. Thank you for watching, and I'll see you in the next video.